Alright, hello. We are going to finish up Chapter 8 by talking about the third section, equilibrium. So we've talked about rotational motion, the different variables that are involved with rotational motion, torque, how to influence torque, and now we're going to talk about equilibrium with rotation. So when we talk about equilibrium, we need to talk about center of mass. So center of mass is the point on an object that moves in the same way that a point particle would move. A really good picture of this is on page 211 in your textbook. But when we talk about point particle, we're just talking about a point. And so every object has a center of mass, and it tends to move in a straight line. To find the center of mass of something, you need to suspend the object from any point, and then draw. So like if you suspended a tennis racket from a string and you let the string hang down, that would create your vertical line. And then, so like, here's my tennis racket. And if I, suspend it from here, let's say I get a vertical line there, and then I'm going to pick another point to suspend it from, and then I'm going to draw a vertical line there. So let's say I suspend it, just to make things easy. It's a great tennis racket. So I suspend it this way, so now I'm going to get a vertical line like that, and this is just hypothetical. Where those two vertical lines meet, that's the center of mass. And so if I take this vertical line and I draw it onto this drawing, then that will put my center of mass right there. And so you could use that to find the center of mass of any object. So where do you think the center of mass is on a human? If you suspended yourself from two separate points and drew two vertical lines, center of mass is just right above your navel or right above your belly button. And center of mass is really important when you're climbing or doing any type of balancing type activities. So when you climb or do things like that, you really have to consider your center of mass. It's not just all about being strong. Well, center of mass also affects your stability. So if you think about tipping a box, it's easier to tip a box that's really tall and narrow than one that is low and broad. And that has to do with center of mass. It's also the reason that certain vehicles are more prone to tipping, like an SUV is more prone to tipping, or like a tall truck versus a small sedan. So if you're trying to tip a box, you're going to pull at the top with a force, which means that you're applying a torque, right? You're trying to rotate it on this axis of rotation. You're trying to move it on that axis of rotation. The weight of the box, which is acting on the center of mass, also exerts a force, which is F of G, and it applies an opposing torque, which we're going to call T of W, or the torque of the weight. When the center of mass is directly above the point of support, so let's say that you have your box maybe tipped, on the edge, and the center of mass is directly above that point of support, the torque due to weight is going to equal 0, which means that the only torque acting on it is what you're applying. When the center of mass is no longer above the base of support, now both torques are acting in the same direction, and it's much easier to then tip the box. So an object is stable if its center of mass lies above its base. And so if we take a look, I thought this was kind of cool. If you've ever seen these type of bottle holders, they work because of the center of mass. And you can see the center of mass is not directly in the center of this object, right? Because it's not regularly shaped. So to tip an object, you need to move the center of mass outside the base of the object, and that'll make it much easier to tip. If the base is narrow and the center of mass is really high, then the object is stable, but it can easily tip over because it's very easy to move the center of mass outside the base of the object. Okay, so we move on to conditions of equilibrium. When we're talking rotational, we have what's called static equilibrium, which means that transitional and rotational equilibrium both must equal 0. Transitional equilibrium is kind of the normal equilibrium that we've talked about so far, where it's the net force exerted on an object, and that has to be 0. Rotational equilibrium is where the net torque exerted on an object is 0. And so you want both of those to be 0 in order to have what's called static equilibrium. Okay, well, when we are looking at rotational motion, we're looking at different frames of reference than something that's linear. So on a rapidly spinning amusement ride, it can feel like you're being pushed to the outside of the wall. Think about that ride, and I've never been on it because I would throw up, but it's going really fast, and then kind of like the floor falls out, and you're on the outside. Well, in this case, your motion's not linear, and so because you're rotating. So rotating frames of reference are accelerated. Okay, just remember when we're changing direction, we're accelerating. So Earth also experiences this because Earth is rotating, but the effects of rotation on Earth are too small to be noticed like in the classroom. But they are significant on the atmosphere, and they can affect climate and weather. Okay, another type of force that we feel is centrifugal force. This feels like a force on the outside of a platform that's pulling on an object. It's not a real force because there's no physical outward push, but you can feel it on rides, amusement park rides, and things like that. We know that acceleration in an object is due to centripetal acceleration, which we can write as v squared over r, or if we're looking at rotational velocity squared times r. Okay, another kind of fake force or non-real force is called the Coriolis effect or the Coriolis force. You probably learned about this in physical science when we talk about like pressure systems and things like that. It's an observed deflection in horizontal motion. And so basically if you're sitting on a spinning platform with someone else and you try to toss a ball back and forth, it's going to be hard to catch the ball because it's going to look like it's tossing to the side. But for someone standing on the outside, it's just going to look like it's tossing straight. And that's because of the rotating frame of reference if you're on the rotating platform. This is not a real force because there's no physical force, but it can affect weather and winds, and it depends on where you're located on Earth. So if you look here, the equator kind of splits this, and north of the equator, you're going to rotate in the counterclockwise direction. Nope, sorry, that's clockwise. And then south of the equator, you're rotating in the counterclockwise direction. And so that can also affect winds and currents and things like that. Okay, we're going to be doing, these practice problems together in class. And then here is the homework, and it's also on your outline. Have a good day.